So welcome students, we're just going to do a very quick lesson on concave mirrors. We're going to talk about their applications briefly and then move on to discussing some ray diagrams for different scenarios. First of all, concave mirrors, where do we use them in our everyday lives? Well, we see them used in shaving mirrors. We see them used on the dentist chair. Dentists use them to magnify images up close. And certainly from this one, it appears as though the teeth are in pretty good shape. We also saw it laid bare when discussing the walkie-talkie building in London. For those that haven't actually read about the walkie-talkie building, it's quite an interesting read, and all the damage that was wrought by the concave mirror. That is the walkie-talkie building. Okay, so ray diagrams for concave mirrors. Well, there's a couple of different scenarios. There is 5 cases we're going to focus on. In those cases, the purple object is going to be moved increasingly towards the concave mirror. So a concave mirror is a curved mirror where in the photo the green represents the back of the mirror, as you would a satellite dish, and the rays are converged. It's also sometimes called a converging mirror because the rays are converged in a point in front of the mirror. So the first scenario that we want to talk about is where the object is outside the center of curvature. Now, what is the center of curvature? Well, the center of curvature is defined by the curve, how curvy the mirror is, and it's basically just the middle point of that circle. So if we were to get the protractor and continue the protractor along, it would be the middle point of our circle. So that's the center of curvature. The focal point is actually halfway between the center of curvature and the mirror. So now that we're familiar with both of those points, let's start drawing the ray diagram. And to do so, we're going to begin by drawing one of the common ray diagrams, which is parallel to the axis being the black horizontal line. So we're going to draw a ray parallel to that, and once it strikes the concave mirror, it's going to reflect back through the focal point. So let's have a look at that. A line gets drawn in, and it's going to reflect back through the focal point. Okay, so it's going to reflect back through the focal point, and we're going to get that eventually. Let's try that again. Okay, so it's going to reflect through the focal point, which will be here. Okay, and remember, it is important to actually show the direction of motion of that image. So it reflected through the focal point. Now, the second image we're going to do actually goes through the focal point, and when it's through the focal point, it's reflected parallel to the axis. So the first one went parallel to the axis, reflected through the focal point. The second ray is through the focal point, reflected parallel. And where those lines converge or meet, that is where your image is going to form. So right at this point, we can see an image has formed. If we now talk about that image in terms of using our SALT, as we talked about today, firstly, the image is, in terms of size, is smaller than the object. It is inverted. Location-wise, it is between the center of curvature and the focal point. And the image itself is a real image. So we would be actually able to project this image onto a screen or a piece of paper or whatever. So it is classified as a real image. Okay, so the first case is when the object is just outside the center of curvature. Now we're going to move on to the second case, and we will find that we can use a lot of the similar rays to discuss what's going to happen. So if the image is actually on the center of curvature, again, we're going to start by doing the parallel ray and then through the focal point. Much better this time. And the second one we're going to do is through the focal point, and it's going to be reflected parallel. Okay, and it's going to be reflected parallel. Now, I know that this is slightly off because when you reflect it parallel, what we should get is an image that is actually same size, inverted, and right on the center of curvature. Okay, so the image itself would be projected and would be in focus right on that point at the center of curvature. It would be the same size, it would be inverted, and that's the second scenario. I should also probably mention that there's lots of other rays that we're only showing two, but there is another ray that you could put here. For example, if it went up and struck the concave mirror, it would actually reflect down at this point also. Okay, so any rays would be reflected and would meet at that point. Another common example is the vertex ray, which goes right into the center. Any ray that hits the center of a concave mirror is treated like a flat mirror because it is quite flat there and would be reflected at that point. So all of these points are going to converge in that spot. So for the center of curvature, it will be inverted, same size, inverted, same location, and it will also be a real image. Case number 3. So for case number 3, we're going to move it in between the center of curvature and the focal point. Again, we're going to try and get some rays that we can use. So first one is we're going to go down through the focal point. Okay, and the second one is we're going to come down through the focal point and we're going to go across. Okay, and what we'll notice here is that we have an image that's outside the center of curvature and it is inverted and it's clearly bigger than the object. Okay, so those rays that we took were the same rays. So into the focal, reflected parallel to the axis, and the ray parallel to the axis is reflected through the focal point. We could have also taken the vertex ray, which we talked about the last time. So I'm just going to show the vertex ray, which goes into the center of the mirror, and then it's going to follow the law of reflection, where the angle of incidence is equal to the angle of reflection, and they will all be at that point. So in terms of salt, you can see it's outside the center of curvature, it's bigger, it's inverted, and it's a real image. I should also mention that if you move this purple point, well, let's see what happens. The actual ray that goes parallel to the axis would still be reflected through the focal point. But now the ray that's reflected through the focal point, I'm going to show it in blue, will actually be in a slightly different location. So reflected through the focal point, it would be reflected down here, and it would follow this line. So the blue line and the green line, you can see that they're going to meet way out here. So the closer that you bring this purple arrow, the bigger that image is going to be. So let's just move the purple arrow back to where it was. I just wanted to show you guys that it would impact the size of the image. Okay, so that's 3 cases. 4th case is where you bring it into the focal point. Now, it is a little bit difficult to start referring to this case because for an image to be exactly on the focal point of the lens is obviously not possible because unless it was a point image. And so maybe we need to drop down the size of this and try and make it a point image. And even still, it sort of doesn't make sense. But let's play around with that. Okay, so in terms of if we make this image really, really small and it's on the focal point, we'll just take two rays as we do all the time. And you'll see that this one here, the first ray, is going to be reflected through the focal point. So it's gone through the focal point, and the second ray through the center, we call the vertex ray. That's actually going to be reflected out, and you can see just visually something about these 2 green lines. At least they should be. They're actually parallel. I know it doesn't look 100% parallel, but it turns out that any of these lines would be parallel. Another type of ray that we can talk about is a ray that goes through the center of curvature, reflects back on itself. So if we put this ray through the center of curvature, we see that it reflects back on itself. So you now have 3 lines. The problem with that is these lines are actually never going to meet. So you're not going to have any image formed. Now, if you were talking about this in the real world, you would actually, you know, if you were to look at this mirror, you'd see an image not clearly formed or in focus. You'd actually see just some colors and some scuffed image. So we say that a proper image, a true image doesn't actually form when the object is at the focal point. So that's case 4. Case 5, the final case, is when we move that object inside the focal point. So what happens, and sometimes students have problems with this one. One of the reasons being is it's much harder to visualize some of our normal rays that we do. Okay, so I'm going to take 2 points, and this time I'm going to start with the same one. Why not? We might as well. Through the focal point. So parallel to the axis, reflected through the focal point. And now I'm actually going to take the center of curvature one. The vertex one. So we're going to put this one into the vertex, and it will be reflected like so. So it's going to be reflected out like that. If we wanted to take the focal point one, we would have to extend to the focal point and know that it would be reflected parallel. So I'm just going to show that. So we're going to extend it from the focal point and then be reflected in parallel. Now this is a little bit unusual because this portion here is not something that that is necessarily obvious. It's a little bit abstract, I guess. But we're starting to notice is now, because this is an abstract one, we can extend this beyond, and all of these points, you can see that they're actually they're diverging. They would not meet on the real side. So we have a line here, we have a line here, and if you extend these lines up, it turns out that they'll actually meet, but the only way that they'll meet is virtually behind the mirror. So if we extend this line on the back, and we're going to draw this virtual object, and we really should draw the virtual object with broken line. Okay, so just so I can signify that it's a virtual object, it will be bigger than a virtual image, rather, sorry. So it is a virtual image. It is bigger than the object. It is upright, so it is not inverted. So let's go through SALT. It is, first of all, in terms of size, the image is bigger than the object. In terms of altitude, it is upright. It's not inverted. In terms of location, it is behind the mirror. And in terms of is it a true image or not, it is a virtual image. So it's the only one that's a virtual image, and that is when the object is placed inside the focal length. We are going to do some practice on this tomorrow. Make sure that you do the accompanying quiz questions, and we'll do some practice tomorrow.